Let me begin with an anecdote from last year. Last year, a lot of the emphasis in generative AI was in experimentation, trying to put together the first set of applications in many enterprises. And in one of these experiments at a bank, they had put out a chatbot and was doing a bit of a field test with a small set of pilot users. And one of those users asked the chatbot, I'm considering getting a mortgage. I'm also considering getting a divorce. Would that impact my mortgage rate in any way? And the chatbot very helpfully responded that you should not get a divorce. It'll have a very significantly adverse impact on your mortgage application. This is the kind of challenge that is very common, as many of you know, as we start trying to go from the phase of experimentation, which was last year, to taking these apps into production, which is where enterprises are this year. It's extremely important to have in place good ways of checking for quality, ensuring that these applications are really trustworthy and they can be managed in production. And that's what I want to talk about today. And in this presentation, we begin with the observation that indeed the era of enterprise AI is now here, but it's still incredibly hard to take these kinds of very meaningful applications and put them into production. And this transition from going from proof of concepts to actual apps in prod which deliver value is very much an ongoing journey. So what are some of the hurdles in moving these apps to production? The three areas that I'll focus on today are: one is quality, two is governance, and three is efficiency. And by quality, I mean challenges around hallucinations, answers being irrelevant, incomplete answers, poor summaries, in the kinds of applications that you commonly see around talking to your data, for example, either retrieval augmented generation-based methods or agentic applications which are starting to emerge and starting to make their way into production. There are challenges around governance, around privacy, data governance, safety, and content moderation, much like our divorce conundrum from a minute ago, as well as security, with adversarial attacks increasingly showing that it's not so hard to have robust models and applications in this area. And finally, cost and latency are really starting to matter. If you want to move apps into production and keep them there and serve workloads with lots and lots of interaction, the OpenAI calls start adding up. So I'll cover two classes of lessons that our team at Snowflake and previously at TruEra has learned in building production-grade apps. I'll use two examples of Cortex Analyst and Cortex Search, which allow talking to both structured and unstructured data, as well as tools and techniques from AI observability around evaluation, experiment tracking, and monitoring. So let's begin with Cortex Analyst. It's a product that's in public preview now. If you want to sign up for a free account on Snowflake, you can play with it. The key challenge and problem that it's working to address is that many times business users want to talk to data and get answers to their questions around let's say, what are the revenue numbers looking like this month relative to the same month a year ago? And usually that involves making use of clunky BI tools or bringing in data teams who help them answer these questions. And that tends to be quite inefficient. So what Cortex Analyst does is to make this much more self-serve, where business users can simply ask questions in natural language. The data teams have to do a little bit of work to set up a semantic model, and I'll explain in a minute what that means. And from then on, the interaction does not require the data teams to be in the loop. It's entirely a direct interaction between business users and the data source. So think of this as a simple way of talking to your data. So one of the biggest challenges in this kind of text to SQL like tools is getting high accuracy and precision. And by that, I mean that it's much better for a tool like this to abstain or say that I don't understand your question or I cannot answer it than to give confident but incorrect answers. So the metric that we will focus on is text to SQL accuracy. And what Cortex Analyst has been able to get to is the state of the art in this area, which is around the 90% mark. If you want to compare it to just using, say, a GPT-4o as a zero-shot kind of question, where you just go to the large language model, ask the question, and then it translates into SQL and comes back, the accuracy for that is around the 50% mark. So this is a very big step up from a baseline using LLM as a building block to an agentic architecture that can start getting to very, very high levels of accuracy. And these numbers are based on an internal benchmark data set that our team at Snowflake had created to reflect the complexity of text to SQL from actual customer interactions. So often in this area, the academic benchmarks from Spider or Bird are used, but those benchmarks are lacking in several different dimensions. The questions tend to be not as complex as real-world situations. This database schemas tend to be simpler and so on. So those are some of the dimensions that went into creating this benchmark. There's a fairly detailed blog post on this topic, which you can look up if you want to get more details. But with that observation, what I want to get into is what are some of the insights and technical approaches that let us get to this level of accuracy. The first is this idea of a semantic model. And it's a fairly simple idea, but it's very powerful and useful. The idea is that you define some of these kinds of filters to say, for example, that whenever you see the word North America in a query, it should be expanded out into, here are some synonyms like the NA region, and then you interpret that, expand it out to be United States, Canada, and Mexico. So when the user asks this sample query in the middle box, which is, what's my total revenue in North America in 2023, you see when it gets translated into SQL, North America got expanded out into United States, Canada, and Mexico. So the semantic model, this is just one example, but the concept of the semantic model is that the text to SQL conversion, the system needs to be aware of the business context, the kinds of words and terms that are used, and having that be a part of the definition of what's made available to the agentic system hugely helps with improving the accuracy. There's a fairly simple interface for data teams using YAML files to specify the semantic model as a starting point. The other key class of innovations here is around starting to bring in agentic architectures into play here. And Mike talked about how agentic architectures are emerging as being increasingly important. And this is a concrete example of a production-grade system that's making use of some of the key insights from the agentic literature. So the workflow here is not just you give the question to a GPT model and it produces SQL. There's a fairly several steps that come together to make this effective. So if we start from the top, you see the classification box. So when the user comes in and asks a query, the classification agent, which is a LLM that's carefully prompted, takes as input the semantic model and the user question, and it first makes a decision on whether this is an ambiguous question, in which case it'll look for related question suggestions and prompt the user to get more specific, or if it's a question that's not answerable in SQL. And it could be like a completely different topic which is out of scope. So that's the first test, and if those tests indicate that more input is needed from the user, you'll get that. Otherwise, it moves to the feature extraction phase. In the feature extraction phase, the agent here is going to look at that question along with the semantic model and try to figure out what type of question it is, using a lot of information that Snowflake has about the nature of data analytics questions. So for example, it might distinguish between time series questions, which are looking at, say, what's the revenue this month relative to the same month a year ago, or aggregation questions, or filtering questions. And those features will then later be used by the SQL agent to, based on the information in those features, it might prompt the LLM differently on how to generate the SQL query. There's also a content enrichment phase, which looks at a set of valid queries, which are already there in the repository. This is where humans in the loop come into play in creating these valid queries, and that information is also used. And then there's some additional things like literal matching and so on that happens in that phase. And then a few different SQL generation agents in parallel might produce like 3 different candidates for the SQL query. Then they go through an error correction phase, each of those independently, which involves calling out to tools, another agentic capability where syntactic checks are done using SQL compilers. There could be other forms of semantic checks there as well. And then the LLMs go through a correction phase based on that input. And finally, there's a synthesis phase where a final LLM agent looks at these error-corrected versions from, say, 3 different SQL generation agents, and then does a synthesis and produces the final query. So the combination of each of these steps really end up mattering a lot in getting us to that 90% mark that I mentioned earlier. There are a couple of blog posts that I will recommend that you look at if you're interested. One around the architecture itself and the next layer of detail on it, and one around evaluation and the nature of the benchmark data set and how it covers some of these areas of complexity that are typically missed in benchmark sets like Spider and Bird. So those were some of the design patterns from Cortex Analyst. Let me transition now to Cortex Search. That's also in public preview. You can play with it if you like. And Cortex Search takes on a related question, but instead of asking these kinds of, providing this capability for talking to your structured data, it provides a similar capability, but to talk to your unstructured data. So think of this as natural language interface for say, customer service chatbots or research lookups or credit analysis reports. And you can ask, essentially, questions of your documents, which is a very common use case. In this area, one of the insights behind Cortex Search is that if you think back a few months, or like certainly last year, a lot of attention was on vector databases and retrieval augmented generation that was powered by vector databases. So that approach is meaningful and is effective, but it is somewhat limited in that it misses out on other kinds of information that's available in keyword search itself. So in this picture, what you're seeing through this hybrid retrieval process, there's the semantic lookup box, which is doing vector retrieval. So queries get converted into embeddings, and then there's a semantic lookup. And then there's a keyword or lexical lookup, which is doing keyword search, which is more like traditional search. And then these produce a set of results. And then finally, there's a re-ranking step, which examines that list of results, re-ranks them, and produces a result. And this combination of semantic search with keyword search and with re-ranking put at the end ends up getting significantly better results than just using one or the other. It starts getting to those elements of quality, efficiency, and governance that I highlighted earlier. In terms of where some of the key innovations here was, the team that worked on this project came from Google and Neva, so there's a lot of depth in search in that team, which just that tribal knowledge and technical depth in that area was very meaningful. But in addition, one other piece of work, a key enabling technology, which is out in open source, is these embedding models. So a key part of this search capability is making use of embedding models that will convert natural language queries and document chunks into embeddings. And the Arctic embedding set of models, they are the state of the art in this field for models of their size. So when Arctic embedding was first released in April of 2024, the large model was beating the performance of models that are roughly 4x the size. And these were closed source models like those from OpenAI and Cohere. So the chart on the right, you can see we are measuring the retrieval numbers with respect to the MTEP data set, and Arctic was beating the state of the art relative to these significantly larger models. Currently, this is September 2024. If you go back and look at the leaderboard for MTEP, you'll see that it's still the top model for retrieval under 400 million parameters. So it continues to be very widely adopted. Just last month, we got over 200K downloads. And if this is a technology that you're playing with, that's interest to you, you may want to check it out. The benefit here is that each embedding model, because it's smaller, it greatly reduces latency and total cost of ownership. Now, at a technical level, under the hood, for people who are familiar with these embedding models, it makes use of these Matryoshka embeddings, which provide very sparse, a very tight, compact representation. And that's one key technical tool. The other thing which really helped Arctic embedding get to this level of state-of-the-art metrics is the way the data is used during the process of training the embeddings. And in particular, data source stratification was very powerful, meaning that when you get data from, let's say, 10 different sources, every mini batch that you're using during the training process always has data from just one source. So you're essentially stratifying the source of data, and the ablation studies showed that that helps quite a bit with improving the performance. And then there's this concept of tuning hard negative mining, which is another kind of technical idea which helps with improving retrieval quality. There is a archive paper on Arctic embeds which gets into all these details. So if you're interested, please do take a look. So with that, I'm going to shift gears a little bit. I gave you examples of 2 production-grade generative AI applications that are very data-centric, that if you have your data in Snowflake, it's very easy to get started with both of these applications. One is for structured data, the other for unstructured data. And for each of these applications, there were technical advances that were made in agentic architecture-based designs, and on the one hand, and on search and embedding models on the other, to really get to state-of-the-art in these areas. A lot of this work is very openly discussed. The Arctic embedding model is in open source, and Snowflake AI research is pushing very much to be building in the open and be a part of the community. I'll shift now towards discussing AI observability and how methods and tools in this area can take the applications that we have put in a good amount of work to build and deploy and ensure that we keep an eye on their quality. We can make gradual adjustments to maintain the quality, keep them trusted, and so forth. So let's discuss a little bit of how things can go wrong. We have a very strong search capability, and search, as you know, is a building block for lots of different applications, but in particular for question answering over unstructured data, RAG-based applications, which have gotten good amount of adoption. But if you look at the architecture of a RAG, there's still a number of failure modes that are common. When you start with your data, the proprietary data that you're using to create the knowledge base, the quality of that data, how you are chunking it, what the chunk sizes are, and so on, matter a lot for the ultimate quality that you get at the end of the day. There are failure modes around search, around retrieval quality, around embedding quality. And then finally, even if retrieval is great, the query has been well understood, in the final completion step, when the LLM generates the final response, it can still introduce hallucinations or inject its own opinions in a way that might be problematic, like in the divorce example. So these are all the different kinds of areas that we want to keep our eyes on as we are developing these applications, and then continue to keep an eye on them as we move them into production. So as we talk to various data and tech teams over the past year and a half in the LLM observability area, and like 5 years and more generally in predictive ML, these are some of the things that stood out, that people are interested in evaluation and experiment tracking to choose components that offer best-in-class quality and cost and latency. By that, I mean that let's say you're building a RAG and you have picked up a particular retrieval system, like a vector database from some company, but you also want to see how the metrics change if you swap that component out and replace it by other choices, like a Cortex Search or some other capability. So for that purpose, we need metrics that can be, and tooling to do evaluation and to track these experiments. Second, when a developer finds failure modes, let's say the metrics are not that great, then they want to understand, get support for debugging so that they can iterate and improve those applications. And then finally, monitoring and guardrail to maintain apps in production. Last year, around May, we released this open source project called TruLens, which helps with evaluation and tracking of LLM experiments. It's fairly easy to use. As you're building your applications in Python, you can add just a few lines of code to instrument the app with TruLens and to add in feedback functions for evaluation. And then when the app executes, the execution trace gets logged and evaluations are computed over spans of that log. TruLens has gotten a good amount of adoption. We get roughly 40K or so downloads every month right now. Last year, I had taught a course with Andrew Ng and Jerry Liu from Llama Index and Andrew Ng from Deep Learning AI, which talks about like a hands-on introduction to using Llama Index and TruLens together. That had gotten about 50K or so signups in the first 3 months. Good amount of interest in using it. In the interest of time, I'm going to just run through some of these slides quickly, but you can go try it out yourself. When you're writing your app, you can see those @instrument decorators. Essentially, you are specifying how to instrument these apps, which function executions need to get logged, and then those will get logged, and then the evals are computed over spans of these logs. We'll share the slides later, but there's a hot link here to a Colab notebook. If you go to the GitHub, there are lots of sample notebooks you can play with. And we have these very nice way of evaluating RAG-based applications based on what we call the RAG triad, which we introduced last year, which very much follows the structure of the RAG. So query, retrieve context, final response. Context relevance is checking, is the retrieve context relevant to the query? Groundedness is checking, is the response supported by the context? And then finally, answer relevance checks, is the answer relevant to the query? So groundedness is particularly important to guard against hallucinations. So when an LLM makes stuff up, the final response will not be supported by the context. And the relevance metrics ensure that it's on point, it's answering the question that you're actually asking and not going off the rails. There's a whole bunch of different types of evaluations that TruLens supports with and without ground truth. On the bottom are the ground truth evals and human evals. This is where normally app evaluation begins. And Cortex Search and Cortex Analyst also made use of a bunch of standard data sets for retrieval and for text to SQL. We talked about Spider and Bird and so on. They're the Baird and MS Marco and Bear data sets. However, when you start moving apps into production, you will often not have ground truth. So you need ways of doing automated evals. We make use of LLMs as judges, as well as smaller models that are more efficient, but require more work for it to work. And that's where we're headed now with providing that kind of support for online evaluation in production, leveraging TruLens. This is a quick example where the question was, when was the University of Washington founded? You see the answer, but the interesting thing which I've highlighted in that box is that it also not just gives the answer, but shows the source that backs that up. There's a bunch of other evaluations to ensure that apps are honest, harmless, and helpful. The harm part would catch things like the controversial answer. And then there's a bunch of ongoing work to make this even more robust, including evals for agents and integration with open telemetry conventions. With that, let me wrap up. There are two classes of insights that I shared today. One around design patterns to improve applications as you're building them, like agentic architectures, like hybrid search, and then general tools for evaluation and experiment tracking and monitoring, which lets you both measure the quality of these applications and to adjust them over time. Thank you very much.